Hello everybody. Today I will discuss the Taylor's theorem. That is the last theorem in this chapter. In the previous classes, I discussed about the Rolle's theorem, then the Lagrange's mean value theorem, then Cauchy's mean value theorem, and today I am going to discuss the fourth theorem, that is Taylor's theorem. Hopefully, this much discussion would be sufficient as far as the theoretical part is concerned in this chapter. Some little bit, few more results and small kind of theorems would be there for discussion, but the large or major theorems will be finished. So today, without wasting time, I'm starting this Taylor's theorem. What does it say? Over here, we are considering the H theta form of Taylor's theorem because it is a bit easier to write just for the sake of expression is concerned, for the sake of simplicity. Okay, so what does it say? It says that the function f, we have a function f in the function in the interval a comma a plus h. And if you recall the previous results, all the previous results in Rolle's theorem, in mean value theorem, particularly Lagrange's form and Cauchy's form, all the results we had two conditions. One condition was that the function f is continuous in the closed interval a comma a plus h, and its derivative exists in the interval a comma in the open interval a comma a plus h. But over here in this Taylor's theorem, the in place of the function f, we have used that the function in n minus first derivative of the function f superscript n minus 1 is continuous on a comma a plus h. Number two, that the derivative of this function, the n minus first derivative of this function, we are again differentiating this one, and then what we get the nth derivative fn. Okay, so derivative of this previous function, this fn minus 1, that means the function, this derivative exists in the interval a comma a plus h. So what we can say that this function is continuous in the closed interval and differentiable in this open interval. Okay, and along with that, we consider a positive number p is a positive integer particularly. These are the three informations or three criteria of this theorem. And if the function f satisfies these results, this criteria, in that case, there exists at least one number theta, where 0 less than theta less than 1, such that f of a plus h is equal to f of a plus h into f dash a plus h square by factorial of 2 f double dash a plus h to the factorial of 3 f triple dash a, and so on. And finally, we get the nth term, that is h to the power of n minus 1 by factorial of n minus 1 if n minus 1 at the point x is equal to a, plus one more extra term. If you count the total number of terms starting from this one, this is the first term, this is the second term. In the second term, we have the first derivative. In the third term, we have second derivative, double derivative. Okay, second order derivative. In the fourth term, we have third order derivative. So over here, this is the order of derivative is n minus 1. So this would be the nth term. Okay, and after n number of terms, we have one more term that is called remainder after n number of terms, and this remainder has different forms. The first form of this remainder is that h to the power of n into 1 minus theta to the power of n minus p divided by p into factorial of n minus 1, nth derivative fn at the point a plus theta h. So this nth derivative is to be computed at the point a plus theta h. Next, one more form is there, that is called the generalized form of remainder. And in this particularly, if you put p is equal to n in this expression, you will get this form that is called the Lagrange's form of remainder. This is actually h to the power of n by factorial of n, fn at the point a plus theta h. And particularly if in this expression, if you put p is equal to 1, then you get the Cauchy's form of remainder. This is the Cauchy's form of remainder, h to the power of n into 1 minus theta to the power of n minus 1 divided by factorial of n minus 1 into nth derivative fn computed at the point a plus theta h. So this is the expression of remainder in different forms. And in probably in the next lecture we will discuss the application of all these results, how to use different kind of remainder in our computation. Okay, so uh, without wasting time, let us first prove this result. And the proof is very similar to the proof of the mean value theorem, but it is a bit laborious, nothing else. Hmm. In the previous proof, we considered a function phi, and the phi function involved a constant capital A. The constant was chosen in such a manner that phi of A becomes is equal to phi of B. Over here B is equal to actually A plus H. So ultimately our target is to satisfy the conditions of Rolle's theorem by the function phi. That means we are going to prove that this function phi is a continuous function in the closed interval a comma a plus h. That is the first condition of Rolle's theorem. And secondly, we are going to prove that the derivative of this function phi exists in the open interval a comma a plus h. And thirdly, we have chosen that capital A is a constant chosen in such a manner that phi of A becomes is equal to phi of A plus h. Okay. Therefore, it is clear that our target is to satisfy the conditions of Rolle's theorem by the function phi. So how to choose this function phi? I am trying to demonstrate the process because this expression is a bit lengthy expression. In exam hall, at least it may be difficult for you to remember the expression. Just I am trying to show you the technique by which I generally remember the expression of this phi function. What we do, we already have the expression of in this Taylor's theorem, the expression of f of a plus h. So forget about this f of a plus h, forget about the left hand side, try to concentrate on this right hand side expression. What we do, if you look at the right hand side expression carefully, I am replacing this small a each and every time the appearance of this small a, I am replacing this small a up to this term, of course. Up to this term, I am replacing this small a by the variable quantity t. Okay, so over here the first term is f of a. I am writing f of t. Over here we have f dash a, so I am writing f dash t, and so on. F double dash a is there, I am writing f double dash t. In this way we continue up to this kind of expression, n minus first derivative of f computed at the point a, and therefore we take in this way this n minus first derivative of f computed at the point t. So just similar to this expression, we are first putting t in place of a, we are putting the variable quantity t. Okay. Now, in order to construct this remaining expression, these coefficients, what we are doing, we are replacing this h, whatever we have, h square by factorial of 2 or h cube by factorial of 2, in each and every coefficients, we are replacing this h by a plus h minus t. You see, over here we have h into f dash a, so this is replaced by a plus h minus t. Then we have h square by factorial of 2. So over here I am writing a plus h minus 2 whole square divided by factorial of 2. In the next term we have h cube by factorial of 3. So afterwards we are writing over here a plus h minus t whole cube divided by factorial of 3 and so on. So finally we have h to the power of n minus 1 divided by factorial of n minus 1. Therefore in this expression we are writing a plus h to the a plus h minus t whole to the power of n minus 1 divided by factorial of n minus 1. Got it? So this much this much can you can construct from the given expression. Hmm. And in the last for this last term, what we do, we are just writing a plus h, this vector, this a plus h minus t whole to the power of p. P is an integer that is already been given in this statement. Okay, p is a positive integer. So we are writing a plus h minus t. This term is actually an exceptional case. So we are writing a plus h minus t whole to the power of p into this constant capital A, where capital A is a constant chosen in such a manner that phi A becomes is equal to phi of A plus h or phi of B. So is this much clear? এইটুকু তোমাদের কাছে ক্লিয়ার কি কিভাবে কনস্ট্রাক্ট করছি phi ফাংশন? হুম, is it clear?
Yes, sir.
Yes, sir.
Sorry, I couldn't follow you. Do you have any query regarding this?
No, sir.
Okay, hopefully it is clear to you. Hmm. So I'm continuing, and this is I'm recording this class. So if you have any further query, you can view this one in YouTube after completion of this class. Okay. Next, so we are given that the function f n minus 1, this kind of function is a continuous function. Okay. Very good. But before that, sorry, I forgot that from this expression, what we have from this expression actually. You see over here, if you put t is equal to a, phi of a, we are trying to compute the expression of phi of a. If you put t is equal to a, so you will get over here f of a. Then if you put t is equal to a, this term would get cancelled with this small a, so only you will have h over here for this factor. You always you will have h. So over here from this first factor you will have h into f dash of a, because you are putting t is equal to a. Hmm. So this expression, similarly you will get h square by factorial of 2 into f double dash a, and so on, etc. Okay, so up to this level, finally in this term you will have h to the power of n minus 1 by factorial of n minus 1 f n minus 1 at the point a, plus this extra term h to the power of p into capital A, and if you put t is equal to a plus h in this expression, you see, if you put t is equal to a plus h in this expression, then the value of this factor would be is equal to 0 at the point t is equal to a plus h. Okay. Therefore, if you put t is equal to a plus h and try to compute phi of a plus h, then from phi of a plus h, if you put t is equal to a plus h, we will have f of a plus h. So f of a plus h is there, but all the subsequent terms, this factor, all the subsequent terms will become is equal to 0 due to presence of this factor. Therefore, the contribution from all the subsequent terms at the point t is equal to a plus h would be is equal to 0. Got it? Therefore, at the point t is equal to a plus h, phi of a plus h would be simply is equal to f of a plus h. So we have this result. We mark this result by equation number 3, and over here you can observe that the result we were trying to prove. We were trying to prove this result. Okay, so this much at least this much you already have proved. If you compare this equation number 3, you have already proved this much along with this much. So this is the extra term that would contribute to construct the remainder Rn after n number of terms. R suffix n refers to the fact that this is actually the remainder after n number of terms. Okay. So now this much computation would be a bit laborious. It may appear that okay, fine, we already got most of this result. Yes, it is indeed true, but the remaining portion would be the computation of this expression in this suitable form, in these different kind of forms, either in generalized form or Lagrange's form or Cauchy's form. This kind of computation would be a bit laborious. That's all, nothing else. It is not much difficult, but it is a bit laborious. So what we need to do, we observe over here that we are given the result that this f n minus 1 is a continuous function. You see, f n minus 1 is actually the derivative of its previous order derivative, that is f n minus 2. If f n minus 2, if superscript n minus 2 is differentiated with respect to t, then you will get f n minus 1. So we can say that this function is differentiable. Okay, and as because it is differentiable, therefore we know that a differentiable function is always a continuous function. So we can say that f n minus 1 is a continuous function in the closed interval f comma a plus h, and by similar fashion we can say all the previous order derivatives up to the original function f. Okay, all the previous order derivatives up to the original function f, all of them are continuous in the closed interval, and of course they are differentiable in the corresponding open interval. Okay, again I am saying that this f n minus 1 is given to be continuous, therefore its previous order derivative would be a differentiable function, and all these previous lower order derivatives would also be differentiable, and so as because they are differentiable, therefore they must be continuous in the closed interval a comma a plus h, and along with the fact that they should also be differentiable in the open interval a comma a plus h. Got it? Therefore we can say that if you look at this expression of this function phi, this function phi involves this function f over here. This is the function f. Then this f dash is there over here. This f dash is there. Then f double dash, f triple dash, and so on up to f n minus 1. Up to f n minus 1, this kind of functions, all these functions are continuous. These all functions are actually continuous function, and we know that a plus h minus t or a plus h minus t square or t cube, whatever you consider, these are actually polynomials. These are actually polynomials. If you expand them with respect to t, okay, in powers of t, you will get some polynomial functions, and all these polynomial functions, including this kind of polynomial functions, all these polynomial functions are continuous and differentiable. Okay, so altogether we can say that the function phi, this is the total function phi should be continuous in the closed interval a comma h, and it should be differentiable in the open interval a comma h. Now is this much clear? এই জায়গাটুকু তোমাদের কাছে ক্লিয়ার হলো কি করে বললাম phi is continuous and differentiable?
Yes, sir.
Clear? বাকিদের কাছে clear
Yes,
তো?
sir.
Okay. So let's continue. So what we have the result that phi is a continuous function in the closed interval a comma a plus h, and it is a differentiable function in the open interval a comma a plus h along with the fact that phi of a is equal to phi of a plus h. So we can say that phi satisfies all the conditions of this Rolle's theorem. Okay, and therefore by this Rolle's theorem we can say that there exists at least one number theta where 0 less than theta less than 1 such that phi dash a plus theta h is equal to 0. There exists at least one number theta where 0 less than theta less than 1 such that phi dash a plus theta h becomes is equal to 0. Now, uh, you see, we need to compute the derivative of phi dash. Hmm. So, this long expression has to be differentiated with respect to t, and ultimately we will find that the most of these terms will get cancelled after differentiation. That is the beauty of this expression. Let's check how to differentiate it, and in order to show it, let me first let me first uh, split the screen. Hmm, sorry. Let me first split the screen tile horizontally. Okay. So where is the expression of phi? This is the expression of phi. This is our phi function. Hmm. And now, okay, this is the our phi function, and over here we are trying to differentiate the phi function. Let's try to differentiate. You see over here, this function phi, the first term is f of t, so its derivative should be f dash t. Now this is this second term is actually the product of two different terms. So we need to differentiate it by parts. Hmm. So this is the first derivative, a plus h minus t with respect to t. If we differentiate it, we will get a negative sign. So minus 1 into the second function. Second function is f dash t. So minus f dash t would appear. Okay. Plus, now the first function should be kept constant. So we are keeping this first factor or first function constant, and the derivative of second function, that would give us f double dash t. Okay, fine. Now in when we differentiate this term, okay, when we differentiate this term, again we face that we have two different factors. One is this factor and another is this f double dash t, the second factor. So let's first differentiate the first factor and keep this second factor fixed. Okay, so we are keeping this second factor fixed, and if we differentiate it, what we will have? We will actually have this kind of expression. I am writing this one for you. So we will have actually this kind of expression: 2 into a plus h minus t, and again by chain rule, whenever this expression a plus h minus t is differentiated with respect to t, we will have a negative sign, minus 1 would appear. Okay, and therefore we will have this minus sign, and again over here 2 will get cancelled with this factorial of 2, so we will have only factorial of 1. So we will have this kind of expression. Okay, so this is actually the derivative of first term, and the second term is kept fixed over here. So we will have f double dash t. Now afterwards, what we need to do? We need to keep this first term fixed. So we are keeping this first term fixed, and then we need to differentiate this f double dash t so that we will get f triple dash t. Now we continue the technique in this fashion, and finally in this last derivative, in this last second last term, not last, this is the last term, hmm, and this is the second last term, we observe that this is again this is actually the product of two functions. This is the first function and this is the second function, so we differentiate it with respect to t. Then what we have? we actually have this kind of expression. N minus 1, we will have n minus 1, and we will actually have factorial of n minus 1 in the denominator. N minus 1 into a plus h minus t to the power of n minus 2, and this expression again a plus h minus t has to be differentiated with respect to t, and that would give us a minus 1, that means a negative sign, that will generate a negative sign over here. And so over here we can cancel a factor n minus 1 from this factorial of n minus 1. So one factor would ultimately we can write it in this way, that n minus 1, this factorial of n minus 1 can be written as n minus 1 into factorial of n minus 2, and therefore this factorial of n minus 1 will get cancelled with this factor n minus 1. So we will have this kind of expression. So this is actually the first derivative of the first factor. This is actually the derivative of the first factor, and this second factor is kept fixed over here. Okay, and in the and afterwards we will have to differentiate this second factor. So if we differentiate fn minus 1 with respect to t, we will get fn at the point t, and the first factor, this factor would remain same. So we are keeping this factor as a fixed quantity, and we are differentiating this term fn minus 1, and we will get fn at the point t. So this much would be the derivative, and over here this is a very simple part, because this second factor is actually a constant quantity. So when we differentiate this expression with respect to t, we will have p into 1 plus h minus t whole to the power of p minus 1. Again, a plus h minus t is to be differentiated with respect to t, so that would give us a negative sign over here. So we have minus p into 1 plus h minus t to the power of p minus 1 multiplied by this constant capital A. Okay. So we observe that phi dash t is this expression, and in this expression it is a very much convenient to cancel this f dash t with this minus f dash t. Again, you see this expression will get cancelled with this expression, and we shall continue. This expression will get cancelled with the immediate next expression. This expression will get cancelled with its immediate previous term. Okay, so ultimately we will have only these two terms in the expression of phi dash t. So next we write that this phi dash t, now let us maximize this one, this phi dash t, this phi dash t becomes is equal to this term minus this term. So these last two terms would appear in the expression of phi dash t. So this much you have to be very careful. You see, there is a scope of mistake, although the expression would ultimately be very simple. Not much difficult, but you have to be very careful in this differentiation process. Okay, so we ultimately got the expression of phi dash t over here, and this phi dash t, in this expression of phi dash t, if we put t is equal to a plus theta h, then we will have this kind of expression. In place of t we are putting a plus theta h, so over here in place of t again we will have fn at the point a plus theta h, and so on. In place of t again we will have minus a minus theta h. Okay, so this would be the expression of f dash theta h, and by this equation number 4, this has to be equated to 0. So this total expression has to be equated to 0. And if we consider this equal to 0, okay, then what we have, we will have the result that you see over here, this a and this a will get cancelled. So we will have h minus theta h to the power of n minus 1. Again, I am saying that h minus theta h to the power of n minus 1. So we can take this h common h to the power of n minus 1 can be taken common. So inside the bracket we will have 1 minus theta to the power of n minus 1. So this total expression can be written as h to the power of n minus 1 into 1 minus theta to the power of n minus 1 divided by factorial of n minus 1 multiplied by this inner derivative fn at the point a plus theta h. And similarly over here, this a and this a would get cancelled. So we can take this h common. So h to the power of p minus 1 would come out of this bracket. And within the bracket, we will have 1 minus theta, this 1 minus theta to the power of p minus 1 multiplied by this constant capital A, and that has to be equated with 0. And from this result, we can compute the expression of capital A. So capital A would be this kind of expression divided by p into h to the power of p minus 1 into 1 minus theta to the power of p minus 1. So we are dividing this expression, this first term by this kind of expression. And what we observe is that this h to the power of p minus 1 and this h to the power of n minus 1, they would together become h to the power of n minus p. Similarly, 1 minus theta to the power of n minus 1 divided by 1 minus theta to the power of p minus 1, this 2 would become is equal to 1 minus theta to the power of n minus p. And the remaining portion, this p and factorial of n minus 1, this would remain be in the denominator. So p into factorial of n minus 1 is there, and the remaining portion, this factor is fn at the point a plus theta h. Okay, so you got the value of the constant capital A, and that is actually a finite number because of the fact that this all these exist, and this nth derivative is also nth derivative exists at the point a plus theta h. So this is actually the value of capital A. Therefore, now we can say that yes, our model by which we took the expression of phi. Why did you took the expression of phi over here? We took the expression of phi in this way, involving the constant capital A satisfying this kind of properties. Therefore, after getting this result number 5, we can say that yes, we get a finite value of capital A. Therefore, our model was a valid model. Okay. And again, if we put the value of capital A in this expression, uh, in this equation number 3, if we put the value of capital A in this equation number 3, then we will have f of a plus h is equal to this much expression plus, let me show you the computation, plus h to the power of p into a. So what we have, this is f of a plus h is equal to this much expression, okay, this much expression plus h to the power of p into the expression of capital A. Okay, and we are writing this entire expression as equal to r suffix n, the remainder after n number of term. So what is r suffix n? Let us compute. Over here h to the power of p is there and h to the power of n minus p is there. So h to the power of p and h to the power of this minus p would get cancelled. Only we will have h to the power of n. And the remaining portion is same, 1 minus theta to the power of n minus p divided by p into factorial of n minus 1 multiplied by this fn at the point a plus theta h. So this is the expression of the generalized form of remainder after n number of terms. Now in this expression, if you put p is equal to 1, in this expression, if you put p is equal to 1, what you observe, just for p is equal to 1, on the denominator we will have factorial of n minus 1, fine, but in this numerator, this 1 minus theta to the power of n minus 1 would be there, and the remaining portion does not change. Okay, and this is called the Cauchy's form of remainder after n terms. Okay, And if you put p is equal to n, p is a positive integer, so we can put p is equal to n. If you put p is equal to n, in that case, 1 minus theta whole to the power of n minus n, that means 1 minus theta to the power of 0 would appear. That is actually is equal to 1. 1 minus theta to the power of 0, that is actually is equal to 1. So this kind of expression would not appear in this case. So what we shall have? We shall have h to the power of n. So we have h to the power of n. In place of p, we are putting n. So we will have n into factorial of n minus 1. That would they would together construct factorial of n. Okay, n into factorial of n minus 1 would construct factorial of n. Let me write over here a multiplication sign. And the remaining portion f n a plus theta h is there. So this is actually the Lagrange's form of remainder. Okay, this is called the Lagrange's form of remainder. I made a mistake. Lagrange's form of remainder after n number of terms. Okay, so that is actually the proof of Taylor's theorem. Now, is it clear to you? Everybody, I am asking to you all. Everybody, is it clear to you? Do you have any question or any part which you could not understand? এমন কি কোনো কোশ্চেন আছে যেটা বুঝতে পারোনি বা কিছু?
Clear, sir.
Clear, sir.
Clear? Okay.
Yes, sir.
Okay. So now I am keeping one result as your homework. That is actually the Maclaurin's form of Taylor's theorem. Okay, in Maclaurin's form, what we do, we actually put a is equal to 0 and h is equal to x. Therefore this interval would be 0 comma x. So remaining proof would be same. So over here, if n minus 1 is continuous in the closed interval 0 comma x, its derivative, that means fn exists in the open interval 0 comma x and p is a positive integer. Then there exists at least one number theta where 0 less than theta less than 1, such that we had f of a plus h, okay, in the left hand side. But now a becomes is equal to 0 and h becomes is equal to x. So we will have f of x is equal to f of 0 plus x into f double dash, f dash 0 plus in place of h we have x. So we previously had h square by factorial of 2. Now we will have x square by factorial of 2 multiplied by f double dash 0 and so on and so forth. Okay. In this way, we will have the remainder after n terms, and these are the corresponding expressions. In place of h, we are putting x, and in place of small a, we are putting 0. So this would be the generalized form of remainder. Why generalized? Because of the fact that by putting different values of p, we can obtain Lagrange's form. By putting a p is equal to n, we obtain Lagrange's form. By putting p is equal to 1, we obtain Cauchy's form of remainder. So that's why this is called the generalized form of remainder. Okay, so I am keeping this statement, the proof of this statement for your homework. Okay, and that would be the Maclaurin's form of Taylor's theorem. And more or less, this portion, the theoretical portion of the end of this total chapter is finished. And let me discuss one problem for you, because you always have a question in your mind that we are going through different theorems, but how to apply these theorems? Okay, so I am going to show you a problem that has been already proved in your class 11 and 12 level, probably using the sign of derivative. We know that if the derivative of a function is positive, then the original function is strictly monotone increasing. So you already proved all this kind of result by the sign of the derivative. But without applying this technique, I am going to show you a result. This is the result. Sometimes it is given in question that by the help of MVT, that means by the help of mean value theorem, you see mean value theorem does not always mean the Lagrange's mean value theorem. It might be Cauchy's mean value theorem. In fact, you will observe that if you put n is equal to 1 over here, I am keeping this observation for your task. You try to reveal the technique or the process. If you put n is equal to 1 in this Taylor's theorem, you will ultimately be able to get the Lagrange's mean value theorem. Okay. So, in that sense, we can say that Taylor's theorem is actually the generalized version of this Lagrange's mean value theorem, and that's why in many books you will find that Taylor's theorem is actually the mean value theorem of order n. Got it? Mean value theorem of order n. Taylor's theorem is also termed as mean value theorem of order n, small n. N is a positive integer. Okay. Now, in this case, we have to prove this result by the help of mean value theorem. You already proved, probably you have already proved this kind of result in your class 11 and 12. It is given that x by 1 plus x is less than log of 1 plus x, and that is less than x for all x greater than 0. We have to prove this result by mean value theorem. And in this kind of result, this is my personal observation that if this middlemost expression is taken as f of x, most of the times if the middlemost expression is taken as f of x, then it becomes very easy to show this entire inequality. Okay, so over here our target is to choose f of x is equal to 1 plus x. Our target is to choose f of x is equal to 1 plus x. Then what would be f of t? F of t is equal to log of 1 plus t, because I told you earlier that our target would always be to choose the variable t and keep this x free, so that we can use this x as a constant or as an end point of the interval, like 0 comma x. Got it? So over here we are choosing, this is the motivation from where we are taking the function x, f. This is the motivation. The middlemost expression should give us the hint to choose the function f. So we are taking f of t is equal to log of 1 plus t for t belonging to the interval 0 comma x. Okay, x is positive quantity. We are given that x is a positive quantity. Now, as because f of t is equal to log of 1 plus x, we need to check whether we can apply the mean value theorem in this function. In your book, actually, directly they have applied mean value theorem, but I have over here I have written all the proper logic, and in your exam at least you have to show, you will have to discuss all this logic, because without logic you would not be able to get proper marks. Okay, so don't give any scope to the examiner to cut your marks. All right. So over here, if we know that logarithmic function is always a continuous function for all the values of t, so we can say that within the interval 0 comma x it is a continuous function. Next, we know that its derivative, we can always differentiate it, and its derivative is equal to 1 by 1 plus t for t belonging to the open interval 0 comma x. Therefore we can say that it is differentiable in the interval 0 comma x. So this much we will have to show, we will have to write in exam at least. Okay. Next, thus we can apply we observe that the conditions of mean value theorem, that means continuity in the closed interval and differentiability in the open interval. These two conditions are true, has been satisfied. Hmm. And therefore, we can say that the Lagrange's, we can apply the Lagrange's mean value theorem on the function phi. So by that theorem, you see, we are considering the Maclaurin's form of mean value theorem. I told you earlier that Maclaurin's form would be helpful to solve the problems. Okay. So we can say that by Maclaurin's form of mean value theorem, we can say that f of x is equal to f of 0 plus x into f dash theta x. Got it? Now, what is f of x? f of t is equal to this kind of expression. Therefore, f of x will be is equal to log of 1 plus x. And therefore, what is f of 0? Just put x is equal to 0 there. So, we will have log of 1 plus x, this is our x, multiplied by f dash theta x. So we already computed the expression of 1 plus f dash t, f dash becomes is equal to 1 by 1 plus t. So we can say in place of t, we can write theta x. So we will have 1 by 1 plus theta x. So that is the total expression. The total right hand side becomes is equal to this first term is equal to 0, log of 1 is equal to 0. So the total expression comes from the second term, x by 1 plus theta x. Okay, so this much was easy. Now the main factor in this kind of problem comes over here. Be very careful about it. Very small part but very crucial part. Hmm. We have the inequality that 0 less than theta less than 1 and x is greater than 0. This is the x greater than 0. This is already provided in the question, x greater than 0. What from this inequality we will have to construct an inequality involving this kind of expression, x by 1 plus theta x, and that inequality would ultimately give us this kind of total inequality. Let's see how to construct this inequality. Okay, so over here we first concentrate on this expression 1 plus theta x, because we already have the inequality involving x, but we don't know what is 1 plus theta x. Okay, so step by step I am moving forward. You see over here x is a positive quantity and this is an less than inequality. So we are multiplying this inequality by a positive quantity x. So as because x is positive, if we multiply this inequality, this less than inequality will remain be a less than inequality. If had x been a negative number, in that case this less than inequality will be converted into a greater than inequality. So be very careful about it. Okay. Now multiplying by x, positive number x, we will have 0 less than theta x, and that is less than x. Now what to do? In order to generate this expression, we have to add 1 throughout this inequality. So I am adding 1 on the left hand side, we will get 1. On the middle term, you will get 1 plus theta x, and on the right hand side, we will get 1 plus x. Now, this 1 is a positive number. So, something greater than 1, that would also be a positive number. So, this is a positive quantity. And this is also a positive quantity. Fine. All of them are positive. That's very nice. Now, what we are doing, we are taking the inverse of this expression, because we need to generate some expression like this, and then it is we'll have then this expression has to be multiplied by x, then we will get this kind of expression. So I am taking the inverse from in this inequality, so that we will have this kind of expression. Okay, some inequality involving this kind of expression, and if we take the inverse, then this less than inequality will be converted into greater than inequality. Got it? Now what we need to do? We need to multiply this expression by x. X is a positive number, so we are multiplying this expression by x. In this line, what I did, actually the right hand side expression, this actually inequality is an inequality involving greater than symbol. Greater than inequality. I am just converting it into less than inequality. Left hand side is greater than middle term, and that is greater than the right hand side. So I am first writing the right hand side. Right hand side is greater than, not greater than, right hand side is less than this middle term. So right hand side is less than this middle term, and this middle term is less than this left hand side 1. Okay, so I am converting this inequality into a less than inequality. Now I am multiplying this expression by x, and so what we get this kind of result, that x by 1 plus x less than x by 1 plus theta x, and that is less than x. Okay, and what is x by 1 plus theta x? You see over here, x by 1 plus theta x is actually log of 1 plus x. So we put over here log of 1 plus x, and that is actually the inequality we were supposed to prove. আমাদের এটাকেই prove করতে বলা হয়েছিল। হুম, so that is the inequality we were supposed to prove in the question. Got it? And this is the proof of the result. Okay, so in this way we can prove these inequalities, and we can apply mean value theorem to prove these inequalities. Probably I have given this file in your Google Classroom. Let me check. I don't remember whether this has been given there. If it is not, I will provide the file over here in the chapter of mean value theorem. Yes, this is provided there. Some typing mistake might be there. I'm correcting over here in this in this lecture. But if you just forget about all this typing mistake, you will get everything in this file. So it is available in this classroom. So I would advise you to go through the remaining portion. Many solved problems are all there, and in the subsequent lectures, I will discuss few more solved problems. Okay. From my end, at least, this much is today's class is finished, and thank you for being patient